We're going to use factoring, or we're going to use whatever techniques, dividing on both sides if we need to, all the things you've normally done with solving equations for years now. But there's going to be a couple of changes. And the changes first is a restricted domain. So we're going to find the angles where the sine of that angle plus 2 equals 3. Only for 0 to 360. On the one, let's see, I think I did one on each page. Once we do that, we're also going to use the same problem, and we're going to find all solutions, meaning not just 0 to 360, but past it to 720 and past it to 10 whatever. Okay, at that point I'm getting my calculator. Or going backwards to negative 360, negative 720. In other words, all possible numbers. And I'll show you how to write that there. And the same thing with the next problem. The difference here is this problem is going to be a simple solve it like just subtracting on both sides. Here we have a square. So we're actually going to do this one as either a quadratic or taking out a common factor. Actually, we'll do both of those on some of these. This one here, I think this one turns out to be a quadratic. And I forget about the fourth one. But you know what? We'll go through and do it. So for this, if I'm going to solve it, I'm going to subtract 2. So sine of x is equal to 1. Okay. Your best friend for these chapters is the unit circle. And you're going to use it. Exactly why I had you do it, and you learned it last year. And why we use it is to find it. What angles have 1 as the result for the sine? So right here, it looks like the sine is 1 at 90 degrees. And 0 here, and negative here, and 0 here, and everything else in between is decimals. So it looks like that's the only place. So there's only one place where the sine of an angle is 1. And that one place is 90 degrees. So the sine is 90 degrees. When the sine of 90 degrees is equal to 1, that point is that x is 90 or 90 degrees. So what we've done here, say what I wanted to, I am missing a page in my notes for it. Oh well. No, not quite. Okay, so that fits inside this restricted domain. So I would simply say x is equal to 90 degrees. This is written in terms of degrees. If I had done this differently and did 0 and 2 pi, that would be telling you that you should, instead of writing 90, you would have to write that x is equal to pi over 2. And then your answer would be x is, and put it inside the brackets. Okay, so I'll just do the pi over 2. I don't really need the x equals in there. So based upon how this is given, you're to write the answer that way. Yes?
Why is the, at the end of the 360, the parentheses not out of bracket?
Good question, because it's always sort of confusing on these. The bracket here tells you you're including the 0. The parentheses here tells you you're not including the 360. It's completely immaterial in this particular one because the 360 and 0 are the same. And that's part of one of the reasons why. There's no reason to make it equal to both of them when they're the same one. So it's like you make it equal with one, and when you come around the other way, it's like you stop there. It's sort of like you include the 0 coming around, and then you stop, so that the next number, so that 360 would be part of the next time around. That's one way to think of it there. Sometimes it's switched the other way more on the whims of the person who wrote the problem, more than anything else. So it's not always, there's not always a specific reason. It's more a matter of checking to see if someone's paying attention to that detail, in case the answer would come up with that number. So there's not a great answer for it. Sometimes it's just sort of the whims of the person writing it. Now, this is the solution in radians, this is the solution in degrees for that domain. If we're going to do it for all solutions, what that means is we're here at 90 degrees. If we went around again at 420, went around again at 424, 50, and went around again and again and again, or went backwards, there's numerous different ones. So what happens is, what you actually have is 90 degrees plus 360, times the number of times that you're going around the circle. So the n stands for as many times as you need to, that you're going to multiply 360. If the n is 1, that means it's 1 360. If it's 2, it's 2 360s. You still end up at 90 degrees. Going backwards would just be like a negative 1. Negative 1 times, negative 2 times, or you can put plus or minus here, we can learn that. But it's really better to keep it plus and let that be the number that changes. So we could go backwards and go back 360 by making that a negative 1 time round, or a negative 2, or a negative 3. And that would account, by putting that n in there, that accounts for all possible answers. You now have an infinite number of solutions because of the fact that you can go around the circle infinitely many times. So I would put brackets around it, and that would be the all solutions answer. So fitting within that domain is just a single answer. In this case, here it's all possible infinite number of solutions, but all matching plus 360a. Okay, now let's look at number 2. We'll have a couple of differences here. One is it's going to be probably 2 answers. You see that because there's a square here, possibly, probably. Also, you see that the domain is different. It's only for up to 180 degrees, but it's in pi, so we're going to put this answer in radians. Right. So, I first look at this, and my own personal first thought is I have a quadratic because I have a square. I'm actually wrong, because there's only 2 terms. Okay, the 0 doesn't count as a term, of course. So what I have here is just 2 terms. I don't have like a plus 5 after it or something like that. What I do have is I have 2 terms with a cosine in them. I'll show you how to think about this by writing this one. Since that's cosine squared x, that means there's 2 of them. Cosine x times cosine x. Because cosine squared x is cosine times cosine. It's 2 of them being multiplied. Minus the root 3 cosine x equal to 0. So what we have here is both of these have a cosine x in them. So I'm literally just going to take out a common factor. I have cosine x coming out. And left over I have this and I have this. 2 cosine x minus root 3 is equal to 0. This is AB equals 0. This is like x times 7y is equal to, say, or we'll say you have x equals 0 and 7y equals 0. You just have 2 separate problems. So we have cosine of x is 0, or 2 cosine x minus root 3 is equal to 0. Separate them. Let's find the places where the cosine is 0. My unit circle. There it is. So the cosine is 0 up here, and when you come down here, the cosine is 0 again here. So that means for this one, in order to get a 0 as a cosine, x would be equal to 90 degrees. Oops, I have to do it in pi, so pi over 2, and 270 is 3 pi over 2. So I have 2 answers there. Take a look at that domain and realize that I'm only allowed to go from 0 to pi. So this one I can just cross out. It's an extraneous answer because it doesn't fit in the domain. Now, it's going to be useful for me later in the find all solutions part, but right now, it doesn't match what was told. This one, now let's solve it by moving the square root over. 2 cosine x is square root of 3 divided by that 2. So let's find where the cosine is square root of 3 over 2. So I see a square root of 3 over 2 here. I see a negative square root of 3 over 2 there. I see a negative square root of 3 over 2. And here's a positive square root of 3 over 2. So it looks like it's at pi over 6 and 11 pi over 6. So x is pi over 6 and 11 pi over 6. Same as the first one, where I look back here at this domain, and I realize that the 11 pi over 6 is outside of the restriction, outside of what I was told. So I can't use 11 pi over 6. Pi over 6 is good, but not 11 pi over 6. So this is saying from 0 up to pi is allowed. Not pi, but up to pi. But that means that these 2 are acceptable answers. Pi over 2 and pi over 6. If I thought about it before I started writing, I'd put the pi over 6 first because it's numerically smaller, but it doesn't really matter officially, so you can get away with it. Now, that satisfies the answer of what angles will make this a true statement within that domain. Let's go one step further to the find all solutions. It's It's going to be the same idea as the last one, where for each one of these, we're going to see about going around the circle, but there's a little twist with one of them. Pi over 2 is here, and pi over 6 is here. So I can put plus 360 for both of them, but these two are now in play. For all possible solutions, those two are now good. I'm no longer within a restricted domain. So I have to take into account the 270 and the 330. Just used to say no. So I have to take these into account. This is my way of doing it. I do a simple little hand graph and then I look at it because this tells me something. This one, I don't have to add 360 or 2 pi. I can just add pi. I can come right over to here. So for this first one, that's pi over 2. If I add pi to it, I include the 3 pi over 2. I don't have to write 3 pi over 2 separately. And I can do it once, add it again, that would be 2, add it again is 3 or 4. I can add it as many times as I want, which is the n. So pi over 2 plus pi n covers half of all of our answers right now. Right? So that's one of them. I put the parentheses, by the way, but you really don't need to when you have those two things together. You'll find I won't use it most of the time, just when I'm talking about it now. This one, though, if I come around here to 330, I'd be adding 60, I'd be adding 300 degrees to it there. But then if I add another 300, I'm coming to somewhere around here. So I can't just do plus 300. In other words, these two are sort of separate. This one I'm going to have to just do 360n, and this one I'm going to have to do 360n. So that means I have pi over 6 plus, not 360, but rather 2 pi. We're doing radians here. So 2 pi n. And then this one's 11 pi over 6. That one's going to be plus 2 pi n. So for these two, we have to do it as 2 pi, because we have to go all the way around the circle every time. For this one, we only have to go halfway around the circle each time in order to get a good answer. Yes?
Could we write plus or minus pi over 6 plus 2 pi n?
I haven't thought about that, but I don't see any reason why not, because the minus pi over 6 is the same as 11 pi over 6, so I think that would be fine. What he's saying here is that this one here is the pi over 6. Instead of going around this way to get to 11 pi over 6, let's go backwards, and that makes this negative 1 pi over 6. And then, by adding 360 to either one of them, that would be acceptable. So this can be plus or minus here, and then these two are good enough. So I think that's reasonable. That would be acceptable, or not doing plus or minus and doing this one separately would be good. So I'll write it up here as pi over 2 plus pi n, and I'll use your plus and minus to save some writing here. Pi over 6 plus 2 pi n. I think one reason I didn't think of it is because it's not that common to see it that way, but in this case, since it works out, that's a reasonable way to write it. Okay. Oftentimes you'll have it where one here and the other one might be down here or over here or something, although depending on where it is, if you can see a way of saving an equation, like going 1/3 of the way or something like that every time, then take advantage of it. Okay, let's take a look at the third problem, page 3. So now on this one, we're going to look at C cosine squared sine squared. First thing I think of is the Pythagorean identity of sine squared plus cosine squared is equal to 1. If I move this here or move that there, though, I don't get the Pythagorean identity. I would get sine squared x minus cosine squared x, or cosine squared x minus sine squared x, and that's not the Pythagorean identity. So that means it's probably not going to work. Instead, I'm going to think of it a little different way. I see I have both of these cosine. If I can make this one cosine also and be combining them, that might be a better way to go, because then I might take out a common factor. So I'm going to play with that idea, which you can sort of tell what I'm talking about. That's probably the way to go with it. Okay, let's see which one I used when I was figuring this one out. Look at papers. Where is my here is this. Okay, sine squared x. So what I'm going to do, and actually I should say, if I move that over here, if I put them as cosine squared and do it minus, I can't do that with it, but I'm still going to take that Pythagorean identity and do it with the 1 part. So remember, this is, that's the Pythagorean identity. If I move this one that way, I get this. So instead of this one and this one being combined together, I'm just going to ignore the other ones and just do that. So by moving this over in the Pythagorean identity, I get 1 minus cosine squared x, and I'm going to just replace that. Plus cosine x equals 1 minus cosine squared x. By doing this, now all of them have the same trig function. They all have cosine. And now I'm going to work on combining them. Let's add cosine squared x to both sides, which makes 2 of these, and subtract 1 from both sides. 2 cosine squared x plus cosine x minus 1 is equal to 0. That looks like a quadratic. That's 2x squared plus x equals 1. And that's something you know how to solve, you know how to put together. So if I actually took this here, and I took this, this would be like cosine x, say I call it y, and I have y squared and I have y. So I have like 2y squared plus y minus 1. Well, that's an easy to solve, an easy to factor quadratic. 2y and I have y. I have to have 1 and 1 here. To make that minus, one's positive and one's negative. That 2 is going to multiply here, so that's going to be a positive, so that's going to have to be a positive, and that's going to have to be a minus. But it's not really y, it's cosine x. So that means this can be factored as 2 cosine x, and cosine x, that's the y's, minus 1 and plus 1. You don't have to pretend it's another letter to do it if you recognize that cosine x is what's going to go here and there because they're going to multiply to it. But it doesn't hurt to do it. It's just one of the methods that sometimes comes in handy for these types of problems. But now that I've factored it, the rest of it now becomes just like the past problems we did. We just solved them for what angle. So I have 2 cosine x minus 1 is equal to 0. Cosine x plus 1 is equal to 0. So let's bring that over here as plus 1 and divide by 2. Cosine of x is 1/2. Here, bring it over as minus 1. Cosine x is minus 1. Unit circle. So the cosine is 1/2. Let's see. Looks like I'm doing with radians again. So the 1/2 is at pi over 3, or 60 degrees. And it's also a positive 1/2 down at 300 degrees, which is 5 pi over 3. So so the angle, the cosine of an angle is 1/2 if the angles are these two angles. And now with the negative 1, so when I look on the unit circle, you get a negative 1 for the cosine only when you're at pi at 1/8. Okay? So that means we're at pi for this one. So we have 3 answers. Let's check the domain. So we're going from 0 to pi. Pi has a bracket. Okay, and the bracket means it's acceptable. You can use pi. So that means this one is going to be okay. Whereas if it was like the other problem where it was the parentheses there, then we wouldn't include the pi. Right? But in this case, it's okay. I made sure that it could be used in this case. But 5 pi over 3 is outside of that. That's beyond pi. So that one goes away. So we only have 2 answers that are acceptable in this one, pi over 3 and pi. Those are the 2 answers that are acceptable inside that restricted domain of 0 to pi, including pi. For finding all solutions, we're going to do the same kind of thing we did before, but now let's take a look at this, and let's figure out, first we're going to include that one back in, and then we're going to figure out what we're going to do. Again, you don't have to like draw a graph of these, or a chart of these, but it's my preferred way where I know pi over 3 is about here, okay? And then 5 pi over 3 is actually down in the fourth quadrant, 300 degrees. Okay. Now, that's an interesting one again because we have a 60 degree here and a 60 degree down. So we have one of those situations where you can do a plus or minus. Okay. We also have pi over here. So I'll take pi first. Pi plus, well, I could do pi plus 3 pi over 2. Okay. Yeah, I could do pi plus the 360n. And for this, I can do plus or minus the pi over 3, because it's up pi over 3 and it's down pi over 3. Okay? And then I can do plus 360n. Okay? Now, having done that, there's another way we can look at it here. Okay, so first, get that down to think about that. Oh, I should have been doing this as 2 pi. Even I'll forget that sometimes, but go back and check and make sure you're using the right domain or the right method, either domain or degrees. Okay. So, with pi, it's a little harder to see something, but I want to put the numbers in here and talk about these for a moment. 60, 180, okay? And then this one over here, we're at 300 degrees. So let's analyze something for a moment. This one here is a difference of 120 degrees. This one here is a difference of 120 degrees. From here to here is 60, and from here to here is 60, so this is a difference of 120 degrees. What you have is not going around the circle of 2 pi every time. What you actually have, if you start here, is you go 120 degrees, go another 120, go another 120. In other words, I'm not going to write it like that at all. I'm going to write pi over 3 plus 120 is 2 pi over 3, so I'm going to say plus 2 pi over 3n. So if I start here at pi over 3 and I add 2 pi over 3, I get to here. Add 2 pi over 3, add 2 pi over 3, add 2 pi over 3, add 2, so on. That's why the n is there that many times. This one expression covers all possible answers. It covers where pi is at 180. It covers the 5 pi over 3 at 300 degrees. And it covers the original 60 because you're going that same distance every single time around. Okay? It's not easy to recognize that, but you should. This is one of those cases where if you don't recognize it, you really ought to. You should be looking for that and try and take account of it. The plus or minus one is, since going the other way around is acceptable, just not common, then I'm not necessarily expecting people to do it. You can if you want to, that's cool. I like the idea too. But this one you should recognize. If you see that you can simplify the answer going in that direction, then do so. Just like where I showed it with the 90 degrees. When, I'll come back for a moment to the other, to one of my other problems. I think it was in the last section. No, it wasn't. It was in this one. Ah, okay. No, no. There's no. Oh well, I don't. Yeah, okay, it is this one. On this one, the one where it was 90 and 270, I did not give the option of doing pi over 2 plus 2 pi and 3 pi over 2 plus 2 pi. I just didn't even give you the option. I expected you, and I do expect you to recognize that, oh, it's going to be just pi each time. In the same way, if you were to see this, I would expect you to be able to recognize that you're going 120 each time, or 2 pi over 3, instead of doing this 3 separate ones, or even 2 separate ones with a plus and minus. So that's the only thing that could be a little tricky, and that's more a matter of analyzing it. Once you get the answers, analyze where it is on the unit circle and see if they're connected. If they're not connected, do them as separate ones. But you want to look and see if they're connected. Okay, the last problem on here. Okay, the last problem has one type of difference to it. Okay, and it's that we have a double angle. So what you've seen in the other problems is a simple solution, a quadratic solution, a taking out a common factor solution, using an identity, the Pythagorean identity. Here we're going to use a different identity. And you have to actually want to see, like this is showing, just recognize that this one is a double angle. So let's look at the double angle formulas and see what it can allow us to do. We have a cosine here and a 1, and we have cosine double angle. Well, we're going to have to adjust that, because double angle doesn't help us do anything until we adjust it or change it. Cosine and double angle, we have 3 different choices. And they're different because this one has both cosine and sine, this one has only cosine, this one has only sine. One of the little keys I gave you before was, if it's possible, try to get the same trig function for all of them. And since we have cosine here, let's try to make this one so it's just cosine. So we're going to use the 2 cosine squared theta minus 1. So that means I will literally just replace that with that formula of 2 cosine squared. And because we're using x, I'll put an x there, minus 1. So this becomes that, and then I do plus the cosine x plus the 1 is equal to 0. Well, as opposed to becoming 1 with the quadratic formula or factoring like that, these 1's cancel out, which sort of simplifies something. We have 2 cosine squared x plus cosine x is equal to 0. And now this becomes like one of the past problems. So what I did is did that, the minus 1 and plus 1 goes away. So I have these 2. This is cosine x times cosine x. So I can remove a cosine x. 2 cosine x plus 1 is equal to 0. 0. 2 cosine x plus 1 is equal to 0. So minus 1 and 2. Negative 1. So by using that double angle identity, I then happened the 1's got canceled out. I had 2 cosines that I could take 1 out as a common factor. I have 2 separate equations, and now I have 2 angles. This angle gives me 0 for cosine. This angle gives me negative 1/2 for cosine. So back to unit circle. So the 0 for cosine is, again, 90 and 360, or I'm back to radians here with pi and 2 pi. So we're only going for the second half here. So here I've got pi over 2 and 3 pi over 2. But this time, we're only between pi and 2 pi, so that one's going to be extraneous. For the other one now, it's negative 1/2. Oh, where is it negative 1/2? It looks like that's at 2 places, second and third quadrant. 2 pi over 3 and 4 pi over 3. So what I'm doing is I'm literally just looking here, finding places where cosine is negative 1/2. And they always match up with each other anyway, so I knew I'd then come down here. Yeah. Well, this one's in the second quadrant, this one's in the third, and this is only the third and fourth quadrant, so that means the 2 pi over 3 is not acceptable. Okay. So we have 2 answers for this one. 3 pi over 2 and 4 pi over 3. Okay. The last part, same thing. Let's identify all the solutions for it. In fact, I should have been making you or letting you just do it. I want you to go ahead and just fill that out and figure out what those would be. Okay? Go ahead and do it and get me what those solutions are. And I'll do it too, but I want you to do it first there. Do it with the n in there for each of, or all 4, or whichever ones you should do it. And we're dealing with radians still, so keep it as a radians one, please. I'm doing it two ways with it, where the pi over 2, because it also, with a pi matches the 3 pi over 2, should be written as pi over 2 plus pi over n, so it automatically includes 3 pi over 2. This one is going 120 degrees or going backwards 120 degrees. But I did tell you already that because doing it with plus or minuses, although perfectly acceptable but not as common, because I don't think you'll see that in the books, in the textbook at all, in that way either, you can do those two as separate ones, as 2 pi over 3 and 4 pi over 3, each of them plus 2 pi over n. So both of these are acceptable this way. This one has to be done that way to include both of those two because it is natural for that. And this one, though it's not as common, is perfectly fine, or just split them up.